Good afternoon. I am Philip Griffiths, a professor in the School of Mathematics and former director of the Institute, and it's a pleasure to welcome all of you for this afternoon's series of mathematical lectures. Our speakers this afternoon are all very distinguished mathematicians who have spent extended periods of time here at the Institute. And I think their work, much of it began when they were members here, reflects the scope and the quality and the opportunity that the Institute likes to provide for mathematicians, especially at the beginning of their career. In your programs, you have short bios of each of the speakers, and since our time is limited, I think I will just very briefly introduce them. After Raoul Bott's talk, there will be a very brief intermission while we change some of the technology. Each speaker will speak for about 30 minutes, and at the end, we'll have, I think, time to entertain one or two questions of comments from the audience. So it's a great pleasure to introduce our first speaker, Sir Michael Atiyah, who is honorary professor in the University of Edinburgh School of Mathematics. Michael?
Well, thank you, Philip, for the invitation. My instructions this afternoon were threefold. First, I should give a talk intelligible to a general mathematical audience. Secondly, it should have some relationship to the Institute. And thirdly, it should be not more than half an hour. Well, I will try very hard to keep to the first of those. I may not be so good on the other two. Now, the topic I'm going to talk about, subject was solitons and symmetry. Solitons are a subject which have emerged in the last 50 years, and I think in many ways are one of the most interesting things that have arisen. They are of interest in many applications in physics, in a variety of contexts, and they also have a very rich mathematical theory. They're on the borderland between mathematics and physics. Now, so the connection with the Institute in Princeton, well, I've tried hard to think of the connections. Most of this work wasn't done here, but symmetry, of course, associated with the name of Hermann Weyl, and we'll see symmetry in a variety of forms in my lecture, in particular also invariant theory, which is what he was associated to. Physics was of interest, of course, to many of the founding members of the School of Mathematics, including Weyl. I mentioned Peter Goddard, the current director. He was, in fact, the person who introduced me to one of the topics I'm going to talk about, which goes by the heading of magnetic monopoles. About 30 years ago, I think I just met him then when he was a young man. I didn't know he was going to be director of the Institute today. And of course, von Neumann was the pioneer, of course, in computing, and computation and the application of computers to mathematical problems is very much involved with the development of this particular topic. Now, in broad terms, a soliton is a solution of a certain kind of nonlinear partial differential equation that, in quote, behaves like a particle. Now, not the kind of precise definition mathematicians usually like to see, but it's sufficiently flexible to cover a wide variety of sins. But the important thing is that it's a wave that looks like a particle, has some of the features of permanence of a particle, and that is extraordinarily interesting in itself. Now, so I said there are many, many important applications in a variety of branches of physics, and it has a lot of interesting mathematics behind it. Now, by walking over to a second machine, I waste time, but gives you more time to think. Now, the traditional solitons that were studied in what's called 1 + 1 dimensions. Now, the fact that physicists write 1 + 1 doesn't mean because they can't add. 1 and 1 means one space, one time. So you're dealing with functions of one spatial variable x and a time coordinate t, and this particular equation, which has soliton features, is very famous and called the Kdv equation for short, because the Dutch name is rather complicated. And it's a differential equation which is written there, and the important thing is that it's an evolution equation in time. You give the initial conditions, and then you can propagate in future time or backward time. And the equation is nonlinear because of that term in the middle that I identified in red. A typical solution of this equation it has a soliton appearance is some kind of bump like that, which you can think of as a traveling wave in a canal, water moving along a canal, propagating in that direction and remaining in that sort of shape. That's looking like a particle moving along in a line. Now this is interest in its approximation to the equations of fluid mechanics, and it can be explicitly solved in a beautiful mathematical way. And the essence of the idea is that you, by some miracle, interpret that function u, which is the height of the wave, as a potential function for the linear operator, just d by dx squared plus u. U is the potential function in here. You forget about time, you think of time as fixed at the moment. That's an operator in x, linear operator. And then you let it evolve in time according to the solution of the Kdv equation. So what you get is a one-parameter family of linear operators. And the marvelous thing is, which you can easily prove by direct computation, is that if this u of xt is a solution of that equation, then this linear operator remains always unitarily equivalent to itself. And therefore its spectrum is unchanged in time. In particular, if it has discrete eigenvalues, those eigenvalues remain constant in time. And those constant eigenvalues turn out to be related to the constant speeds of the various solitons in the equation. It's a beautiful fact, rather miraculous. That's why I've put some exclamation marks. And once you've realized this, then of course you're in the business of using all the strength of linear operator theory, spectral theory, applying vast amount of machinery of a linear kind to help understand the nonlinear equation. That's the beauty of the theory, and you can essentially solve this equation completely, all properties about it, and there's a vast literature on this subject, which I'm not going to go into detail at all, but an extensive theory, and important thing is that there are these conserved quantities, the eigenvalues. They're conserved quantities, and physicists know, ever since Emmy Noether pointed out, the conserved quantities correspond to conservation laws in physics, and conservation laws correspond to symmetries. So when you see a lot of conserved quantities, you say, aha, symmetry, Hermann Weyl. And the symmetries turn out in this case, they're called hidden symmetries because they're not transparently obvious in the beginning. And they turn out to come from a Lie group, which is hidden in the background until you find it's there, and it isn't just the usual 2x2 matrix group. So there is a Lie group in this theory, and from that, all the beautiful results follow. That I've compressed into, 5 minutes or less, a vast amount of work, extraordinary interest, and the Kdv equation is only one of many equations that exhibits all these properties for which there are associated theory depending on a linear operator. Now I'm not going to talk about that because I couldn't give a whole lecture to it, because I want to talk about some larger class of solitons which exist in more dimensions. So I'm going to move up fast from 1 plus 1 to 3 and 4. And I'm going to talk about solitons in 3 and 4 dimensions. Now in 4 dimensions, there's one famous example which comes from physics and what are called instantons. These are solutions of certain equations that come from physics called the self-dual Yang-Mills equations. And these equations were brilliantly exploited some years ago by Simon Donaldson in purely mathematical context, not in flat space, but on curved manifolds, to prove fantastic theorems about 4-dimensional geometry, which, amongst other things, got him a Fields Medal. This is a marvelous application of an equation, soliton-like equation, which came from physics and was applied in geometry. That's in 4 dimensions. I'm going to focusing more on 3 for the purpose of this lecture. And in 3 dimensions, the equation I'm going to talk about, first instance, is the equation that governs these things called magnetic monopoles that I told you I learned from Peter Goddard. Now, both these 2 equations, the equation that governs magnetic monopoles goes by the name of the Bogomolny equation after the Russian mathematician, and is very closely related, in fact, to the self-dual Yang-Mills equations in dimension 4. They are intimately related, and the same techniques that can be used to solve one can be used to solve the other. And it turns out, if you're working in flat space, R4 or R3, depending on the case, that the key idea, the key step in the solution is to use the theory of Roger Penrose of what are called twistors. Now, I put a star here to remind me to tell you how I found out about twistors, because that was also the Institute for Advanced Study. And well, in a rather perverse way. I was visiting the Institute, I was shortly going back to Oxford, and in the meanwhile, Roger Penrose had just been appointed to the chair of Oxford. And I was talking to Freeman Dyson, and he said to me, oh yes, Penrose has done some marvelous things about black holes and gravitation, very impressive stuff. But he said he's also done some funny things to do with things called twistors. I have no idea what they are, but you're going back to Oxford, you might be able to find out. Well, it was actually a very good remark, because when I went back to Oxford, I knew Roger Penrose from the old days, we were fellow students together, and, you know, after a while he explained his ideas, and it turned out I could understand it very well from a mathematical point of view, and the subject flourished. And amongst various other consequences, the applications to these equations came out as a kind of byproduct, and you have a beautiful theory of how to solve the complicated equations that I haven't written down here, which lie behind that. It's nonlinear equations involving 3 dimensions, not just 2, and there is more or less a complete theory of these, very parallel to the theory in 1 + 1 dimensions. In particular, there is a sort of use of complex variables, very analogous to what comes into the scattering theory for linear operators. And interestingly enough, there is a linear operator associated to these equations, but unlike the other case of the Kdv, this linear operator is not pulled out of a hat. It's naturally part of the physics of the problem. It is nothing else than the Dirac operator associated to the physical background of the story. So you don't have to invent an operator. It's there, given to you by Dirac. And if you use that operator in a certain way, then you can, the theory of that linear operator enables you to solve these equations in a marvelous way. And that's been extensively developed. I'm not going to go into the details, telling you the sort of potential results. Now, the interesting thing is that these equations in 4 and 3 dimensions, this particular equation, really there's only one equation in dimension 4, and the one in dimension 3 comes from it, these actually can then be reduced in dimension. If you have an equation in many variables, independent variables, you can specialize down to when solutions are only dependent on 1 or 2 of them. That way you get equations in lower dimensions, smaller degrees of freedom, much simpler problem. And you can do this in many different ways, depending on which set of coordinates you choose to ignore. It turns out that practically all the equations in 1 + 1 dimensions that can be solved by these marvelous techniques all can be obtained from this one single equation in dimension 4 by different choices of dimensional reduction. And not only can the equations be obtained in that way, but the techniques for their solution, the linear operator, and all that goes with it, exactly come down from above down below. So this equation in dimension 4 is kind of the master equation, which all the other equations really are special cases. And so this higher dimensional theory is beautiful because it's A, natural, and B, it uses very powerful complex variable techniques in higher dimension, but it includes within it all the detailed theory on the lower dimensional case. This dimensional reduction story was originally put forward by Richard Ward, and there is actually a book by Mason Woodhouse, all of whom are students of Roger Penrose, which explains this whole program. Now, the aim of this talk is not to go into detail at all about the equations, but to tell you certain features about them. In particular, the second part of my title is about symmetry. I've already mentioned symmetry in the context of the Lie groups, which are hidden behind here, and there is a Lie group in these theories here. But I want to talk also about other symmetries, namely the symmetries, the finite symmetries that correspond to the Platonic solids. You know, tetrahedron, cube, icosahedron. And you might ask, why should one be interested in looking for solutions which have such symmetries? Well, you're in 3 dimensions. It's rather natural to look at nice solutions, and you might just say it's an amusing exercise to try to find beautiful solutions. But it turns out there are actually better reasons than that. But let's take first face value that we're trying to find simple solutions of complicated equations. Symmetrical ones are, in some sense, nice and simple. Now, let me tell you what is a magnetic monopole, and in broad terms. Now, the history of this goes back to the work of Dirac himself, who postulated what would happen if you studied an isolated source of magnetism, a point source of magnetism like a point source of electric charge. Maxwell's equations are essentially symmetric between electricity and magnetism. So just as you can imagine a point source of electric charge giving a spherically symmetric radial field, so you can just flip it over, think of a magnetic monopole as it's called, giving a magnetic field. These things don't exist in nature. You get dipoles, but Dirac said, let's suppose one exists, what can we deduce from it? And he made very important deductions as a consequence of using that idea. Now, the solutions of course, the Maxwell's equations that correspond to a point source are, of course, mathematically bad because you have a singularity at the source. All a source is a singularity. But it was discovered some years later, when modern non-abelian gauge theories were developed, that in this context, where the theories are nonlinear, whereas the Maxwell's equations are linear, then somehow the nonlinearity can help you to eliminate singularities. And what you find are soliton-like solutions where, so to speak, you get localized large effects in the region which in the linear equation would have a singularity. You smoothed out the infinity and spread it around. And that's not done by hand, it's done for you by the differential equation and the nonlinearity. So, of course, they attracted a lot of attention in the physics community. These things are somehow beginning to look like some kind of particle in a physical context of 3 dimensions, and therefore they're worth studying. So these are the things called magnetic monopoles. Now, a little bit more about them. The actual equations that you write down are rather complicated, difficult to solve. There is actually a slightly simplified version of the equation, which I talk about, which the physicists introduced. I won't explain where it comes from, called the BPS model, where the equations are more tractable and share the common features of the original physical story. And this equation can be written down, and I'll describe it for you. The data of this equation is in 3-dimensional space. Give yourself what a mathematician would call a connection for an SU2 bundled over 3 space, and what a physicist called a gauge connection. In other words, gauge potential. This data is called here A of x. X is a point in R3. A is a connection. It has indices 1, 2, and 3. It lies in the Lie algebra of the group, and that's the potential, or the connection, if you're a mathematician. In addition to that, you also have another field called the Higgs field, which is a scalar with values in the Lie algebra. By the way, the Higgs field is very important in current physics, and in one model or another, people are looking hard to find the famous Higgs particle out in CERN. They get building big accelerator, and if they find this big particle, my colleague Peter Higgs in Edinburgh will be very pleased indeed. But he's getting on in life, and it takes a long time to build accelerators, so touch and go where they'll find it in time. Once you've got the data, the field, the potential A, then what you can do first of all is construct from the field the curvature, which is called the field for the physicist, the gauge field, and then you write down the equation, which I've written here, which just says that the covariant derivative of the Higgs field, that's what this d sub A means, is the dual of the field strength, of the curvature. This duality is just the duality in 3 dimensions between something with one component and something with two skew-symmetric indices, and it just says that this one form is dual to that 2 form, with values in the Lie algebra. It's a very simple equation, it's natural geometrically, it's the equation that comes from the physics. So this is the nonlinear equation you're studying. The nonlinearity is present because the curvature coming from non-abelian group has a quadratic term in it. You put, of course, boundary conditions, any equation worth studying. The boundary conditions you require are that the field falls off at infinity, it goes to 0, and that this Higgs field, which is a vector in the Lie algebra of a 3-dimensional group, so it lies in 3-dimensional space, should have a norm going to 1 at infinity, a certain constant which you can normalize to be 1. These are the boundary conditions, and then in this situation you have an obvious topological invariant, namely, if you look at the behavior of this function phi at large distances, it's approximately on a unit sphere, and it's a function of the large sphere of large radius in R3. So it maps a 2-dimensional sphere to a 2-dimensional sphere, and that has a topological degree, an invariant. That topological invariant is, you fix that, I mean, once you've got the boundary data, that's determined for you, and that is interpreted physically as the magnetic charge of the system. So the simplest case is we take k equal to 1, that would describe a sort of basic monopole particle, and k equal to 2 would be 2 particles, k equal to 3 would be 3 particles. I mean, solitons come originally as single ones, and then they come in trains, 1, 2, 3, 4. So it's always interesting how they interact. So studying this problem here, which arbitrary integers k, is an example of looking at soliton-like behavior. Now, there are, in gauge theories, as physicists call them, there's an ambiguity. The gauge potential can be changed without changing the physics, or for a mathematician, what that means is you have to worry about automorphisms of the bundle. And you only are interested in studying solutions which are equivalent up to these transformations. So your problem is, mathematically, you have a differential equation, you want to solve it with given boundary conditions, identify solutions when they differ by an equivalence. And that's your problem. And the answer is, turns out that there's not one solution, there are finitely many parameters for the solution. The solution space is a manifold, it's called a moduli space, and it has a dimension that is approximately 4 times k. Approximately means there are some technicalities to do with base points which I will ignore, following examples yesterday, sweep things under the rug, and the solution is, answer is that you have a 4k dimensional manifold of solutions. And these 4k parameters can be, roughly speaking, interpreted in physical quantities as the degrees of freedom of your solution. If you have k particles, they sit in k positions, that's 3 times k, but each particle has a kind of little phase variable, a circle, that gives you another k, and so you get 4k. And that's a good description when they're very far apart. When they come closer together, that's not the right way to count them, but the mathematics takes care of that. Now, there's a very beautiful theorem which comes out of this twistor theory of Roger Penrose, which says that this manifold can be explicitly identified. You can prove a very beautiful theorem that this manifold MK of solutions, which parameterize the solutions, is nothing more than the space of rational functions of a single complex variable of degree k, and a map of the two-sphere to the two-sphere, which is holomorphic of degree k. That space is the parameter space. So it's a beautifully simple space. Now, this is a rather deep theorem. It's not easy to prove, and moreover, it's not easy to use. If I give you a rational function, it's not at all easy to write down the solution. You know it exists, but there's no explicit way of getting there. Nevertheless, it's a very powerful description of what all these solutions look like. Now, let's tell you what happens. Let's take the first case. If you take the simplest kind of rational function, just fz equals z, identity map if you like, that corresponds to the basic monopole of charge 1. And that solution, as you'd expect, is a spherically symmetric solution, giving something localized around the origin, a nice spherically symmetric solution. And you can write it down explicitly, it's quite simple. So the basic solution is easy to write down. Then you can look at k equal to 2. What happens if you have to try and solve for 2 particles? Well, you write down a general rational function of degree 2. Well, the simplest one you can think of is fz equals z squared. And this one has, obviously, exosymmetry. You can multiply, you can rotate the solution. It's invariant under rotations. So what you find is that you have a solution which is axially symmetric. This axial symmetry corresponds, when you look at this actual solution as a sort of distribution of charge, if you like, or energy, you get something in the shape of a torus, which has a minimum at the origin and is distributed in a ring around that. Now, that's the case of a special solution. A more general quadratic function would be something z squared minus c. You can put it in that form. And if c is large, then you're describing 2 things which are very far apart, approximately distance c. And then you get locally something that looks very much like the single monopole. When you bring them together, what happens is that they merge and form a ring. And I'm going to show you a picture in a moment of what that happens. And one of the interesting things, and one way it's interesting to study what happens when things merge and collide, is you might be interested in, at the moment I'm talking to you about static solutions. There's no time in this problem, but there is a time you can insert, and you may want to study what happens as these collide under moving in slow motion, moving slowly, and then they will scatter in some way, and that's the kind of thing you might like to know. And so there is, in fact, a very beautiful result, which follows more or less from understanding what happened in the collision state, which this picture here is supposed to describe. You have 2 particles, top and bottom, indicated schematically by spherical blobs. Of course, these are schematic. They have a tail that decays very far away, but this gives you a picture of where most of the energy is concentrated. They come together in a direct collision path. As they approach each other, they bend around into kidney-shaped things like that, and at the point of collision, so to speak, where the parameter c goes to 0, they form a beautiful ring, indicated in the middle. If you go on beyond this, what happens in the outcome of this collision is that ring now breaks in half, but then in a perpendicular direction, like this. And the 2 particles scatter at right angles. So it's a very interesting process by which you get what's called 90-degree scattering. And it turned out this is something which happens in a variety of systems, and they're always sharing the property. In the collision state, you get a toroidal shape. Well, that's the case of k equals to 2, and it's a very interesting phenomenon. If I had more time, I could have shown you a beautiful video, which was made for me many years ago by IBM, and it's a nice 10-minute video. I didn't bring it with me because you didn't give me time, but it's actually rather fun to see what happens, not only for direct collisions, as you vary the parameters a little bit and get more interesting collisions. Now, now a little bit of invariant theory. If you've got a rational function of degree k, that's a holomorphic map of the sphere to itself, or to another sphere of degree k. It's particularly interesting to look at the branch points, places where the derivative vanishes. The sphere is the complex plane, so this is classical branch points in complex variable theory. And if the map is of degree k, a little bit of calculation with Euler characteristics tells you that you will get 2k minus 2 branch points. And in algebra, you don't have to write this down. You write the rational function in terms of two polynomials, p and q. You think of the polynomial as homogeneous in degree k in two variables, t0 and t1. You form the Jacobian, as it's called, which is the 2 by 2 matrix of partial derivatives. The partial derivative knocks down 1 in degree. The 2 by 2 determinant then gives you a 2k minus 2 polynomial, which is called the Jacobian of the original pair, and that, or the rational function, and that's a good example of a classical invariant, the sort of thing you can read about in Hermann Weyl's book. Now, so if you have a rational map, the most obvious thing you can associate to it is a set of branch points. If you're interested in finding a rational function which has some symmetry, under some finite group of symmetries, then of course this finite set of points should be preserved under these symmetries. So if we're interested in looking for solutions that satisfy Platonic symmetries, we have to find a group that preserves that set. Now I'm going to give you, well, I'll come back to that in a moment. But now you have a fundamental question of invariant theory, if you like. Given a rational function, you construct the Jacobian, but given the Jacobian, can you reconstruct the rational function? If so, in how many ways? If you do a little bit of check on how many parameters they depend on, you'll find they both depend on the same number of parameters. The rational function is really a pencil of quadratics, and that corresponds to a line in the space of quadratics, and that's the dimension of those of the Grassmannian, which is 2k minus 2, and the Jacobian is a polynomial of degree 2k minus 2, so you can find the same dimensionality. You expect to be able to solve the equations. With any luck, you might hope to get a unique answer. And let me give you an example, the case of k to 3. One of the things I learned from my good collaborator, Raoul Bott, is that you should always do a simple example. The audience may not understand anything at all about the general lecture, but they might follow an example. So here's a nice example. You can't get simpler than that. Take k equal to 3, so we're dealing with degree 3 polynomials. The Jacobian has degree now 4. So we're associating to a pencil of cubics a quartic polynomial, the Jacobian. Now, being a geometer, I like to interpret this geometrically rather than algebraically. I was brought up as a classical geometer. So in geometrical terms, what you have is the following. In particularly three-dimensional space, you can think of that as representing the coordinates of a general cubic. You have a line, this green line. That's a pencil of cubics, and the ratio of two members of that is the rational function. You have, on the other hand, a distinguished cubic curve corresponding to the perfect powers. And given this rational function, the Jacobian, geometrically, just means the tangents that meet that line. There are 4 tangents to this curve that will intersect that line. So the converse problem is, given these 4 tangents, how many lines are there? Well, elementary geometry tells you that 4 lines in space have in general 2 transversals, because 3 lines determine a quadric. The 4th line meets the quadric in 2 points. There's a single generator of the opposite system through each point, and you get 2 transversals. And when you ask, well, for particular solution points of this, do these 2 coincide, and when do they coincide? Well, nice little exercise for you, and I mention this because I hope you won't mind, but I proved a theorem a long time ago when I was a very young man, and the first theorem you ever prove is your love of your life, okay? And I proved this when I was an undergraduate in 1951, and the theorem is simply this, that 4 points on this curve have a cross ratio. We know points on a predictive line have a cross ratio, one invariant, and this cross ratio may be a special of one kind or another. There's a special class called one which is equianharmonic, and that interpreted simply says that the 4 points are really the vertices of a regular tetrahedron. It corresponds, if you like, 4 points give you an elliptic curve. It corresponds to the curve where the lattice of the elliptic curve is hexagonal. Anyway, the theorem is simply that the 4 points have a unique transversal if and only if they have this tetrahedral symmetry. So if you take the 4 points to be points of a regular tetrahedron, then it turned out there's one and only one rational function that corresponds to that. And therefore, there is one and only one magnetic monopole with that symmetry. That's a nice little application. You can write it down in equations. If you write down the rational function, here it is. You can find similarly rational functions which have octahedral and icosahedral symmetry. They're a bit more complicated, but here they are. So you can write down, for each of these, there is a monopole with those symmetries. Now, if you're good at doing computer calculations and pictures, you can find what they look like, and here's what they look like. Or forget about this one here. I go to 3. Now this is a tetrahedral picture. That's the octahedral symmetry of the cube, and this is the icosahedral or dodecahedral symmetry. Now these describe what? These pictures describe, in the first case, you have degree 3 monopole, 3 monopoles. If they're very far apart, they look like vertices of a triangle. You bring them together, and in the collision state, what happens is they jump into space, and they form themselves approximately into a tetrahedral shape. And what's surprising is, of course, that these are not 4 particles, they're 3. When they get together, they somehow have the symmetry of 4. Similar thing with the other numbers. If you have 4, you get 6, and if you have 6, you get the icosahedron. So these are things that you get exhibiting beautiful symmetries for these solutions. Now, half an hour is obviously not enough. I have a nice lot of things I was going to tell you about, but there's clearly no time for them, so I think I better have to stop, or the chairman will call me to order. But I should just make one comment in conclusion. This is a particular problem which you can solve because of the beautiful mathematics in it. But there are other closely related or sort of similar type of problems where you can't solve. There are no explicit solutions known. But nevertheless, by some comparisons with this one, and by a bit of ingenuity, and a lot of computer calculations, you can actually show that they have similar types of solutions. In other words, these pictures of tetrahedra, dodecahedra, and so on, are not unique to this particular one. They are sort of, if not generic, occur in a number of examples. Same as it was happening with the 90-degree scattering I gave you before. There are things you can learn about in a particular example, where you can do it explicitly, and then it turns out, some reason we don't understand, they are part of a more general pattern that applies in other contexts. And that's a lesson one can learn by doing a combination of analytical techniques, computer methods, numerical calculation, and a bit of physical insight. I don't provide the physical insight, that's my friends, and other friends do the computing. I help with the mathematics. Well, as I said, time is short. Half an hour is hardly enough to get going, really. I'm just into my stride, but I have to stop now. Okay, thank you.
Thank you, Michael. I think we have time for 1 or perhaps 2 questions or comments.
Did Einstein speculate about solitons? Solitons didn't really hit the scene until after Einstein died. I mean, there are rudiments in the past. Solitons were sort of discovered back in the 19th century, but the real modern theory took off only after the computer came along. People could do the calculations and see them. And that happened just shortly after the first papers on this appeared in the 60s, I think. So I'm sure Einstein would have loved them, because there are soliton models of black holes and all sorts of things.
Okay, I'd like to once again thank Michael for a beautiful talk. While our next speaker is coming up to the podium, if anyone by mistake got a dark olive coat last night, about 3/4 length men's coat, if they could give that to one of the Institute staff out in the front hall, that would be much appreciated. Our next speaker is Professor Raoul Bott, who is Professor Emeritus in the Mathematics Department at Harvard University. Raoul, it's a pleasure to welcome you.
Well, it's quite a crowd here. It's a great honor to be brought here all the way from California on this very nice occasion. I came here, of course, 56 years ago, and to a large extent, I think my benefactor who brought me here was Hermann Weyl. George Dyson yesterday informed me that he found the paper where they were selecting the people for admission that year. And he found my name on the list of doubtful candidates. So I was a candidate that had not been informed that they had been accepted, but they had not been informed that they had not been accepted. Yeah. So I decided that, as usual, between my two friends, I'm talking that I'll be on the lighter side of this subject. And after the imposing stuff Mike was told, I think you'll find my talk much easier to understand. And coming back to Hermann Weyl again, he liked to sit with us young people up in the little restaurant, and then he would often say, "Oh, you poor people, mathematics has become so complicated." Especially, I remember he once mentioned Fritz Hirzebruch's Riemann-Roch theorem, which he thought was unbelievably complicated compared to the mathematics that he himself had done in his life. And he would give examples. And so the title of my talk is really what Marston Morse missed by not talking to Hermann Weyl, in a sense. And it was my good fortune to sort of to pick up on there. So I came here as an engineer, and topology was a pretty difficult subject to understand, but questions of this sort I was able to understand. So according to Morse, if you had a function on a manifold, you should look at its critical points and count the critical points by how many directions of steepest descent came from it. Now, even as an engineer, I knew what that was. So, for instance, I learned the following picture. Here is the two-sphere. You take a point outside and look at the distance function. Then, of course, it's easy to see that the critical points correspond to the places where the straight lines meet the thing at right angles. And so the two critical points are here and here. Here is the minimum, and here is the maximum. And here is a wonderful point, the center of the circle. You notice that these 2 points are the symmetry, one takes into the other. And this is the minimum, this is the maximum. And this is what in geometry is called the focal point of this shape along this line. And it's of course means because all these normals come together here. And so in the Morse counting of this function, you would write down a 1 for this and a t squared for this, because there are two directions of steepest descent, independent directions, and this would then be the Morse counting function of this function. And the nice, and to me I immediately loved this theorem, that his theorem was really that if you do this in general on a manifold, this function of course depends on the original function, the counting function, but it satisfies certain inequalities. But more than that, if you're lucky, then the inequalities become equalities. And in particular, for instance, if all the exponents that you find are even, then automatically this function is a perfect, as we call it, perfect Morse function. Well, this is what I would sort of call the baby, what we used to call the baby Morse theory. What really fascinated me was that he had, and that was of course also to a large extent his fame rested on this theorem, that for instance he proved that there are an infinite number of geodesics joining any 2 points on a sphere. And he used the Morse theory there in the following way. So the problem was, so the theorem is that you can do the same sort of thing if you study the function on the loop space of a manifold. That means you take a manifold M and you study all the paths that join a point P to Q. You take the energy along that path, and the extreme of that are the geodesics. And you can count the geodesics by their critical points. And they turn out to have the marvelous property that the number of negative directions is always finite. And so you can formally write down the same sort of series. So let's, for instance, do that for the two-sphere. Again. So we start here, and we choose a nearby point Q, and we start to study the critical points of this situation. Well, you see, the geodesic segment, here is, of course, a geodesic, but that's not all. You can also go this way. You can, of course, also go this way, and so on. So you see that there's an infinite number of critical points immediately. And you can write down the Morse series very easily, because it turns out that what is the focal point there in this situation becomes a conjugate point. And the conjugate points are precisely, the conjugate points of P is precisely the antipode and P itself. And so instead of looking, Morse's very beautiful so-called index theorem said that to count the number of negative directions, you just have to count the number of conjugate points along each geodesic. So for instance, if we do this, you will see on the two-sphere, you will see that this thing here counts for 1. This fellow here, I don't see quite from, yeah, this fellow here crosses the conjugate point once, so it adds a T, and then you'll find one that they add one more each time we go around, so you get this series. Now this series, actually the way it stands, would only satisfy inequalities. Actually, if I write it, it's 1 over 1 minus t. It's a shorter way of writing it. So here we don't know whether this is really describes a Poincare polynomial of the loop space. But actually one could show that it does. But certainly if I'd switched to a higher sphere, if I'd switched, let's say, to the 3-sphere, then it's fairly easy to see that these multiplicities change. And so then you would have had, for the 3-sphere, the corresponding 1 over 1 minus t squared. this would be the answer, and this would prove that the cohomology of the space of loops on a sphere has this Poincare series. So I think that was a wonderful result, and it's interesting that when I was here in Princeton, the topologists pay no attention to this, really. You know, I mean, and never did I hear on Fine Hall anybody comment on this fact, which is completely ignored. And this was, of course, in 49. Then, of course, Serre appeared in 51 or so, and suddenly loop spaces and so on became the bread and butter of all of us topologists, but in a quite different way, not in the Morse way. And before Serre, nobody thought it was interesting that one could compute the cohomology of such interesting function spaces by such easy geometric computations. All except me, I must say. I enjoyed this very much. So, is there an eraser here? Can I erase? I guess not. A bit terrifying. Oh, thanks. So when I left the institute, went to Michigan, and there I started to learn about Lie groups. And as Michael was saying, one loves one's first theorem, so that's the one I'm going to talk about, which I discovered there in the about 52 or so. So as I learned about Lie groups, of course, I came to appreciate this picture of the two-sphere in a different way. The two-sphere is the adjoint orbit of the SO3 group of symmetries. And so when I went home, and as I say, in Michigan, I started to think about the next group, so to speak, SU3, which is a three-sphere. And then I saw right away that we had already computed the Poincare series of the three-sphere. So we were on the way. So, sorry, SU2. SU2 really, Morse's way of computing gave the cohomology of the loop space of the three-sphere. And so the next step was to look at SU3. And now, the marvelous thing is that you see in the orbit of SU2, the two-sphere intersects this line in just these points. Well, there's a corresponding phenomenon in all Lie groups, has to do with the Cartan subalgebra, but in this example, it has to do with that you have a two-dimensional plane, and if you take the orbit of anything in the adjoint representation, it will intersect that two-plane in a similar way in which this orbit intersected that line. And in fact, what you find then is that if you take the matrices then, 3 by 3 matrices in SU3, or diagonal matrices, and write down the lines where two eigenvalues are equal, you will find a picture of this sort. And if you take the orbit of any point here, the marvelous thing is that you'll find this orbit is perpendicular to that two-plane, and it hits it, comes back, once in each one of these symmetry places. So the orbit goes out and comes back. So if you study the distance from a general point, let's say, to the orbit, then you easily check that the critical points of their functions are precisely these intersections. So there we found only 2. Here we would find 6. And more than that, if we draw the lines, just as here, you remember we had the minimum when we didn't hit a focal point and the maximum there. Here the number of negative directions at the corresponding critical point is just the number of times you cross these lines. So that means that this thing would be 2. This would be 2. This 4, 4, and 6. So that the Morse series of this adjoint orbit would be 2t squared plus, what am I doing here? 2t plus 2t to the 4th plus t to the 6th. And lo and behold, they were all even. So this is the actual topology of an orbit in SU3. And now this thing here is the, how should I put it? The marvelous thing is that this happens for all these compact Lie groups. The picture is the same. This is called the Wahl group, of course. This is the Lie. You have to look only at the Cartan subalgebra. You have the Wahl group. The general orbit, adjoint orbit, is actually parameterized by the elements of the Wahl group. And these indices that I've written down geometrically, the algebraists usually like to write down as the number of negative weights that have been changed by an element of the Wahl group. So this was, I think I was the first to notice this. And it was great fun, and it started to make me think, well, maybe we can do the same thing for the loop space of the Lie group. So, and as it turned out, you can indeed. So this is where this picture will come in. This is, unfortunately, the blackboard is too small for me. No, but we have enough room here. Now what is this? You remember I just showed you in SU3, in the Lie algebra, in the matrices of trace 0, 3 by 3 SU3 matrices, the places where 2 eigenvalues were equal. Now you can actually look in the group at the diagonal matrices and draw on the space of diagonal matrices, which is a two-dimensional torus, all the places where 2 eigenvalues are equal. And then you take the universal covering of that, and you get obviously this picture. And this picture has additional information, namely, if this is the origin, then here is the lattice that and so on. So I recover now, on the plane, I recover the picture of this diagram, as it's called, of the Lie group on the maximal torus. And I get a picture of this sort. We get a lattice together with planes called the root planes. but they now form a tessellation of the whole plane. And now the beautiful thing is the geometry comes into the fact that in a Lie group, if you start a geodesic in a general direction at the origin on a torus, it will stay on the torus. So that the only geodesics that join two close by points, which are in general positions, you can actually see them as straight lines on this universal covering. So if you, for instance, if this is the origin, and I'm looking at the space of paths which go from here to here, then here is the first geodesic. But of course here is another one. Just like in that earlier picture of what I was drawing there, you get a very beautiful linear picture of all the geodesics in question. And so you have to then only count, again, try and find the directions of steepest descent. And you find, just as before, as you might conjecture, that if I draw, for instance, this geodesic, I just have to count the number of times it crosses the planes and multiply by 2, and that gives me the number of negative directions. So I have a complete picture of all the geodesics joining two general position points on the Lie group. Now you fiddle a bit about this. There is an obvious, the symmetry group now is larger than before. So I can now do the following thing, that I can try and keep track of this situation more systematically. And this is called a positive chamber in the Lie group industry. So you choose a positive Weil chamber. And then obviously every geodesic can be rotated into this one by conjugation. So I can take these points which are spread all over and always rotate them back into the fundamental chamber. And the beautiful thing is that I completely fill out this chamber, so that I don't have to draw these cues so carefully anymore. I can indicate them by just, so there's a Q here, there's a Q here, there's a Q here, a Q, so on. So I just, well, the positive Weil chamber is here. And so if to each one of these, there is a unique geodesic that corresponds to it, and I can read off its index. Now, because the index is given by counting how many lines you cross, let's do that here, for instance. So this is, of course, this is called an alcove in the industry. This alcove represents 0. Here, the Q that was in here, you get to with crossing just one line. So here you put a 2. Here you put a 4, 6, and so on. So for SU3, you see that the Poincare series, and now notice because they are even, this already actually computes the cohomology. And so the answer is, if you do a little counting here, this line gives you 1 over 1 minus t squared. And then you can repeat this. Once you have added all these together, you can add these lines, and there you notice that you always go up by 4. So it is times 1 minus t to the 4th. And that, of course, is the correct answer. And this way of getting at it proves that there is no torsion in the space path on the Lie group, and that was at the time unexpected, because, of course, the Lie groups, the higher Lie groups, do have torsion, but they lose it all in the step to their loop space. I don't know how much time have I got left? So, all right, so this now you can see quite easily how it extends to the classical groups. This sort of information about the Lie group is precisely the sort of information that is used in classifying them, and so it was very easy to write down the corresponding formula. Let's actually, for those of you who don't know, let's compute this way what the loop space of G2 is. You know, G2 is a more sophisticated object, which most people don't know so well, but I know there are some people interested here. I don't know, do you know the Poincare series of the loop? Well, if you look at the so-called diagram of G2, it's very easy to obtain it from the one of SU3. I mean, these pictorial methods, of course, only work, alas, for groups of rank no greater than 2. But G2, thank God, has rank 2. So all you have to do is add these lines to I hope I'm missing a few. Uh-oh. Maybe I have enough now. Here, you see here now the Weil chamber would be like this. And it's these shapes that play the role of the alcoves. And so I start here with 0, 2, 4, 6, 8, and you'll find that the first time I get something else is 10. Here I have 2 10s joining. So the loop space of G2 is 1 over 1 minus t squared, 1 minus t to the 10th. And so as far as the homology of the spheres that underlie it, they would look like a 3-sphere cross an 11-sphere. And well, this was great fun for me to find out, because I knew nothing about G2 at all. But the world at that time didn't know anything about the topology of G2. And from this one could immediately decide that, for instance, pi3 was the infinite cyclic, and that the next homotopy group was 11-dimensional. Well, so this is to show you what, as I say, Morse missed. If you had talked to Hermann Weyl just a little bit, right? This is really, it was all completely in his grasp. I mean, he could have done this in a moment's time. But we all, unfortunately, tend to miss these opportunities. At this stage, I could really start a longer lecture. because these diagrams, of course, you should think of them as little what sticks out in an iceberg, because since the period I did this, a tremendous amount of information has been found out about, in particular, about this situation. You notice that this, to me, it already was clear, this looks very similar to my original computation in the Lie algebra situation. And I could never, and here you notice that this loop space seems to be made out of many copies of what I found in the infinitesimal picture. Well, all that has been completely cleared up in the meantime. This marvelous world of the Kac-Moody Lie algebras, their diagrams, their topologies, the representation series. That to me was a very exciting moment when really the whole classical representation theory of the compact groups suddenly was lifted up and extended to the Katsumudi algebras and the representations of positive energy. These things came as an impetus from physics. And of course, they've had their repercussions in not just in this context, but in algebraic geometry and even in p-adic theory. But I think that's all I have to say. Thank you.
Thank you, Ralph, for a beautiful talk, and I think we have time for one, perhaps two questions or comments.
I'm always very clear. Oh, no, my, oh, that trouble.
Did Morse and Weil talk at all about other things?
Well, Morse was, in some sense, a sort of, he communicated only outward. No, I didn't see him palling around with any of the professors very much, but he was a wonderful, although he was domineering in that sense, he was at the same time rather humble and you know, for instance, and very informal. On my 26th birthday, he was invited to a little party we had on the thing, and he immediately challenged me to a race to the nearest tree. Yeah. But the only people that I saw talking in an easy way to each other were really von Neumann and Hermann Weil. And really of the permanent members at the time, Hermann Weil seemed the most at ease here and was a wonderful presence.
Okay, thank you, Raul, again for a beautiful talk.